Okay, so today and tomorrow we're going to talk about graphing, and we're going back to some fundamental graphing skills that we learned way back in middle school. Graphing with a table. Graphing with a table is the very first thing you learn to do way back in middle school. You have an equation, y equals something with x in it. How do I graph it? I make a table with x and y. I pick my x values. I use the equation to calculate the y values. I plot the points on the graph. Yeah, very first graphing skill you learned. We're going to do the same thing with polar equations. Yeah? So we're going to do this with the example that we just used in our warm-up. R equals -2 cos theta. Yeah. And the very first step is to make table. Yeah. Choose your input values. Calculate x output values. Words are hard today. Calculate output. When we're dealing with x and y values, we had y equals a function of x. We knew that x was our input, y was our output. We chose the x values. We substituted them into the equation. The equation spit out the y value that went with it. Looking at that equation there in polar form, which variable is serving the same purpose that x did in our previous Cartesian graphs? R or theta, which is in the same place the x would have been. Theta, yeah, theta's over here. I'm going to pick a theta value. I'm going to shove it into that cosine function. I'm going to do -2 cosine of whatever theta I pick, and then the equation is going to spit out an r value that goes with it. And that's not necessarily obvious. That's why I asked, right? That's what we're talking about. So just like we make our tables x, y, we fill out the x. Now we're going to make table theta r. We fill out the theta. We use our calculator to find the r. Yeah? So everybody has a calculator handy? If not, you should have a unit circle, because we're picking values off a unit circle. Actually, let's do it where I can see that graph. We'll do it sideways. Okay, so my default when I'm plotting polars is I go 0 to pi, and then if that's not enough for me to see the pattern, I tack on extras. So 0, let's do 30, 60, 90, 120, and 180. I think that's, I feel like I'm missing one. 120, 150, 180. There we go, 150. All right, so starting with 0. To find r, I use the equation. So I'm going to do -2 times cos of 0 degrees. What is negative 2 times cos of 0? Negative 2. Very good. So first point on my graph was going to be 0 degrees, negative 2. Good. I should put degrees there. We're going to repeat this process by substituting in our chosen angle. So the next one's going to be negative 2 cosine of 30 degrees. I am going to put a couple minutes on the clock. I want you to fill out the rest of that table. If the values are decimals, round to the 10th place. Use your calculator. Fill out the rest of that table. Round to the 10th place. Brittany, what did you get for negative 2 times cos of 30? Negative 1.7. Very good. Liliana, what did you get for theta is 60 degrees? Negative 1. Very good. Melissa, what did you get for theta is 90 degrees? 0. Very good. Alexis, what did you get for theta is 120? Positive 1. Very good. Daniel, what did you get for theta is 150? 1.7. Very good. Nati, what did you get for theta is 180? 2. 2. Perfect. Perfect. That's exactly what I got on my calculator. Yay. Very good. Step 1, make the table. Any guesses what step 2 is going to be? Same as it was before. We're going to plot those points, yeah? This time you need to plot it on a polar graph. Not an XY graph. You'll notice the graph I have up here is a polar graph. Yeah. We saw this last week. So when we plot polar points, we start with the angle, we figure out which angle we're on, and then we move out from the origin to where my R would be. So for that first point, we're at 0 degrees, so I'm on the x-axis, and it says negative 2. So negative 2 would be right there. That is the worst point I've ever drawn, right there. Yeah. And we're just going to go around the picture using, oh my gosh, no, that's right, I was right. 30 is here, yeah? And it says negative 1. So 30 degrees, start at the origin, go back 1. So 30 is that guy there. Oh, not 1. 30 is 1.7. Why did nobody say anything? 1.7. There we go. Next one. I start at 60 degrees, so that's this guy. Yeah, 60 degrees, and I go back 1. So 60 degrees, follow it through the origin and go back 1, which is right there. Next one's less scary. 90 degrees, I'm at 0. So that's a point at the origin. The rest are positive, they're less scary. So at 120, I'm at 1. At 150, I'm at 1.7. And at 180, I'm back at 2. that looks kind of like a hexagram. It's got 6 points, but this is a smooth curve, doesn't have sharp edges. If I were to connect those dots in a smooth curve, we get exactly what we predicted we would be. That's a circle. And if we look at that circle, edges at 0, edges at 2, the center is at -1, which makes sense because the equation was originally this. And I know this tells me horizontal shift, back 1. So we took the center from the origin, shifted it back 1. Circle has a radius of 1. That matches exactly what we learned about circles with Cartesian points way back in chapter 1 of pre-cal. But the equation is less scary with polar. Turns out that all of the graphs, that's not what I meant to do, that are a constant times cosine or a constant times sine are all going to be circles. The sine function by itself plots a circle. The cosine function by itself plots a circle when we're looking at polar coordinates, because it cycles from positive to 0 to negative to 0 and back to positive. It forms a closed loop when we look at what the y coordinates do for sine. Okay, so the process. Are we comfortable filling out a table of values using a calculator? I see nodding. Yes. We practiced plotting points last week. If I give you a blank polar graph, are we okay plotting points? I see nodding, as long as you have a blank polar graph. Good. Okay, so that's time consuming, and it's 2025. We don't want to do that if we don't have to, which is why humans invented graphing calculators. So let's talk about what this process looks like on your graphing calculator. So next thing we're going to look at, we're going to do an example equation. We're going to do it with our calculator. I want to plot the polar equation r equals 2 plus 3 sine theta on my calculator. The first thing I need to do is tell my calculator that the things I am putting in y equals are polar and not Cartesian. So the very first step to graphing on your calculator is you are going to press the mode button. And when you press the mode button, beneath radian degree, it should say function parametric polar SEQ for sequence. So you want to set your mode to polar. So you go down to the function parametric polar sequence, you highlight polar, you press enter. Yeah. What that does is it now tells your calculator that instead of y equals some stuff with x, you're doing r equals some stuff with theta. The next step is to go to the function edit menu, which is y equals. And in the y equals menu, enter your equation. When you go to y equals, you should see R1, R2, R3, R4, yeah? So you're going to enter your equation in R1. So you should see R1 equals, you're going to type 2 plus 3, and then you're going to press the sign button. And then I want to pull up a theta. Where is the variable button on my calculator? I'll give you a hint. It's the same button we use to pull up an x. Where's my variable button? Not second. How did we pull up an x when we were graphing? Very good. Xt theta n. That's the generic variable button. X for function, t for parametric, theta for polar. We're automatically in polar. It's automatically going to put a theta on your screen. Xt theta n. Yeah. That button's right beneath the mode button. Yeah. Once you have entered your equation, you are going to press the graph button. And ideally, you get a nice, pretty graph. You may need to change your zoom settings. Yeah. My recommendation, if you get a funny looking graph that doesn't quite fit on your screen, is to press the zoom button and then select zoom fit or zoom standard. When you go to zooms, you won't see zoom fit. You have to scroll down. It's off the screen. And I see some nodding. When I did it, I got a picture that looked like this. That's a horribly drawn, but that is the shape of the picture, yeah? Okay. So y equals R2 theta. And you don't have any of your plots turned on. Oh, you have a stat plot on. Oh. There we go. Let's turn all the stats plots off. Oh, okay. It's too zoomed in, so we're going to go down to zoom fit. So yeah, it's just... Oh, and that's ugly too. Let's do zoom standard, which is option 6. There we go. Okay, wow. Yep. When in doubt, zoom settings. This, by the way, is called a limicon. I don't know what that little looks like a C but is not a C symbol is, because I really haven't studied a language that uses that in its vocab. I will have the correct pronunciation for you tomorrow. But we're going to see several patterns as we graph these polar functions. We're going to see circles. We've already seen them. Those are the sines and cosines by themselves. We're going to see cardioids. We're going to see limnicons. We're going to see lemniscates. We're going to see roses. We like the sound of that. And we're going to see an Archimedes spiral. Everything except the last one, an Archimedes spiral, closes in on itself. Most polar graphs form a nice closed shape. It may have petals like a flower. It may curl up on itself like this guy does. But most of what we're looking at is nice closed shapes. When I see you tomorrow, we're going to start matching equations to names so we can identify shapes by looking. Yeah? You have homework due today from last week, homework 15. You have homework posted for next week, due Monday, week 16. Bolther and Delta Math, Some of you have smelly grades in my class because you haven't done any of your homework. Please go back and do the delta math. I will give you full credit for it. Just get it done.